Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. We have been discussing the important topic, the method of weighted residuals as an approximation method for a problem given in the form of governing differential equations. This is, in a nutshell, this is what we have been discussing. So this is a very important part of finite elements. And so we are going to discuss it in 1D, 2D, and then there are various variations of this problem, of this formulation. So let us look at, actually we were talking about the fundamentals of weighted residuals. And wherein, just to recall, is that if this is the governing differential equation together with the boundary condition here, so what we say is that we are going to find an approximate solution for phi, and if it is phi hat, so this part will not be identically satisfied, and then that's going to have a residual, an error, or called a residual. So this is the residual part, which is non-zero within the domain omega. And then what we do here is that it is pre-multiplied with another function wi, and so then it is integrated over the domain omega, and then we said that this should be 0. Okay. So in the limit, obviously phi hat is the solution, so this is going to be 0. But on the other hand, so let us look at phi hat, and what we said that phi hat is going to be approximated as phi hat here is a function of xy, and we said that we are going to approximate it in this manner. So that this satisfies the boundary condition here, and if m phi hat plus g is equal to 0, then the condition on this one, if you put m here on both sides, so at where a is the undetermined coefficients which we are going to find. So this is going to satisfy, if this is going to satisfy like this one, and so these are the conditions on psi naught and psi j. So this is psi j is a set, and we say that obviously you can see that if you put m for this one, so that m phi hat plus g is equal to 0 for all values of ages. So this is the important part. So whatever be the ages, so this assumption is going to satisfy if psi naught is going to satisfy the non-homogeneous part of the boundary condition, and psi j's will be the homogeneous part of the boundary condition. Okay, so that m phi hat plus g is equal to 0. So this is, by this way we are satisfying this boundary condition for all values of aj, and what remains is the satisfaction of this one in an approximate manner. So if this is going to be non-zero, so then by multiplying with wi and then integrating with omega, so we will get, knowing the functions wi, again an assumed set of functions, and they're called weighting functions, and we are going to get as many equations as necessary here. So since phi hat is going to have n undetermined coefficients of ages here, So we can formulate n equations here by taking n different weighting functions. So yesterday we were also talking, just to recall, that this is similar to our vector algebra, where if you say that an unknown vector R, if its dot product is taken in x-axis, that's meant dot I, or y-axis dot j, and z-axis dot k, if they are individually 0, then R has to be identically 0. So that's exactly what's being done here in the space of functions, functional space, where whatever residual you have here, you are taking it as an inner product with some function, and then you say that its component or its projection on Wi is 0. So if it is Wi is a complete set of functions, then you maybe the n tending to infinity. So in the limit, then the ages, the equations which you are going to get in ages are going to determine the solution exactly, or in the limit, right? So this is what we are, the theory behind this method of weighted residuals. All right, so this is theoretically it is fine. So now let us see how these things can be written in terms of algebraic equations. So what we mean is that how to get n equations in the set AJ, right? So let us see how. So how do we do that? So yesterday, the Wi, we also mentioned that these weighting functions, if they are same as the assumed trial functions, sizes, then we call it as Galerkin method. If the Wi is different from the set psi I, then we call it as a Petrov-Galerkin method. So let us, so that is some difference, looks to be small, but sometimes it assumes an important aspect of the approximation. So let us see how we can derive now the algebraic equations. So for that, so let us take this equation. So substituting in weighted residual statement. So what we are saying here is that this is the integral over Wi. Wi is a function of xy itself. And here we say that this phi hat, we will write it as phi naught plus aj ij, right? This is about L. And then we also have f here. And the whole thing is integrated over the domain. So this d omega is an elemental area for the domain omega. So it can be dx dy, or it can be r d theta and dr. So depending upon the kind of coordinates which you use, or dx dy dz. So let's try to expand this one. And if you expand this one, so let's collect these things. L psi naught. And the second one here, there's a summation here. And this L operator will be acting on psi j because aj is constant, and there's a wi. So summation will take it outside, and wi L psi j. Okay, so this is the second part here. And then that's also leaving one term here, wi is equal to 0 here. Okay, so this is the expansion of this one. So here, let's collect these terms. So here, sorry, there is one aj here, right? So let's collect the terms on one side, and this one, Aj, Wi, L, Ij. This we keep it on the left side, and we'll take the other ones on the left side with, of course, with a negative sign here. And then we also have so why we collected the terms on the left side and right side is that on the left side, so this is the one which we are having as unknown quantity, and this is, of course, knowing Wi and psi, you can integrate it about the domain omega, and this is obviously is going to be a function of g. So these terms are functions of psi j, and the left on the right side we have these terms which are constant in the sense that given Wi, so all these things can be calculated to be a given different value, right? So this is depending upon this. So this is, we call it as ith equation, and you can have as many equations. You can assume the weighting functions as many as you want. Say, for example, here you can have n equations, and then you can formulate n equations. So these equations can be written like this in the matrix form. So for example, this is a set of coefficients an, and this is bin, and we call this as in the usual conventional sense, we call this as some K matrix here, K11, K1n, and then there is a Ki1, I2, In, Kn1, N2, Nn. So this is so this can be put in the form, in the matrix form, like this, and so this equation, ith equation, corresponds to the ith row with these coefficients a1 to an, and on the right side we call it as bi. So here, if you see it carefully, the K matrix is the general matrix which we use the term. Please don't get confused this K with either the conductivity or any other material property. So this is generally what we follow. K. Later on we use the term stiffness matrix, so it is more similar to that. Just to keep that kind of terminology, we are using K, but otherwise people use A matrix. So all right, here, so if you can carefully look at that, the Kij here, the general term, is nothing but Wi L Ij, right? And so this is a general term of Kij, and the right side Bi can be identified as, it is simply Wi L psi naught and minus Wi F. Okay, so this is where you can identify these terms Kij and bi. So it's very nicely. So the whole problem now comes down to simply finding out this quantity Kij, a general term. Obviously, Kij depends upon the weighting function Wi as well as the trial function, set of trial functions psi j. And so this will be giving you the value Kij, whereas Bi is again a value which is depending upon Wi and psi naught here, Wi and F, which is of course the heat generation in the body, or it has many other connotations. So whereas in the case of membrane, which we are going to take up later, so it might even be the load. Okay, so this is in a nutshell. So now there are so many equations. So finally, this will turn out to be this. So once you can very easily see that once you formulate this matrix K, so then these are the undetermined coefficients. So this is known vector. So you can do the matrix manipulations and then get the solution for A, right? And once you know A's, then you go back to this expression for phi hat. So that means that knowing all Aj, knowing all the trial functions Ij's and psi naught, so we are going to have the solution. Okay, theoretically this is in a nutshell what it is. Of course, obviously it depends upon Wi also. So the Wi can be same as psi I, so which I was mentioning, or another set, another complete. So this first one is known as Galerkin method of weighted residuals, and this is Petro-Galerkin Okay, so this is in a nutshell. The whole method of weighted residuals can be put just in this form of algebraic equations, right? Okay, now let's continue this one, and let's illustrate this one with respect to a problem. Okay, so let's do a small problem here, a example here. To the example of a membrane under situation T and subjected to a uniform load Q. Of course, we are taking Q in a positive sense. And of course, the geometry of the membrane is of rectangular shape. So in the rectangular shape, so what we mean is that so it is a size of 2 in this direction and 4. Okay. So if this is the membrane, and we know that the equation for this one will be, let's say, since we are using phi, let phi is equal to phi xy is deflection, in which case the governing equation will be So we said that all these problems come under the same Poisson's equation. And the equation is dou square phi by dou x square plus q by. Okay, so this is the governing equation in the domain omega. So omega is what? So it is minus 2 plus 2 x direction minus 1 2 plus 1 in the y direction. Okay, so that's the omega part. And the boundary condition here. So it is supported on all sides. Simple boundary condition supported on edges, all sides. So this is the boundary domain. So let's say that phi is equal to 0 on the boundary. And of course here, remember that Q is the applied load. Q is uniform load, uniformly distributed load. Okay. Then, so if you, what is our first task? So our first task is to determine psi. So to determine psi naught. So the, what will be the psi naught to start with? So psi naught, the boundary condition here is that phi hat has to be 0 on boundary. In fact, we put it as m phi plus g is equal to 0, which is most general. It may also have a derivative boundary condition. So here in this simple case, so if phi hat has to be 0, then we can say that very clearly that psi naught has to be 0, right, for all values. And what about psi j? The set psi j. So the set psi j has to be equal to 0 on. So this we say that homogeneous type of boundary condition. All right. So if this is the case, then what is the suggested values for these functions? So we can have the polynomial set of functions, or we can even have a trigonometric type of boundary condition. So you can see here, so these on the boundary, the function has to be 0 for z, while it has to be some function, non-zero function in the domain omega. And you can see that here we would like to choose something symmetric functions. So why? The problem is symmetric. So if it is being acted upon by, so if I just draw an isometric view of the problem. So, and then if it is acted upon by load here, uniform load of intensity. So this is all, let us say, vertical load. And you can see very well that the problem is symmetric, geometry is symmetric about xy axis, as well as the load is symmetric about xy axis. Then we know that the solution also will be symmetric, in the sense that if you just see the x part, for example, so a cross section here, if you cut it anywhere here, so we know that, well, now I just write it like this. It is supported on this side and at the two ends. So at the two ends, at x is equal to -2 and +2, it has to be 0. and then it will take some value like this one, and then it should be symmetric. In fact, you can also have some other values like this one, but all of them should be symmetric about x is equal to 0. So the kind of functions which you can suggest for x is equal to 0 symmetry are the trigonometric functions of cosine nature. So for example, cosine, so let us say pi x, pi by 2, x by 2. So this is, for example, this is nothing but cosine pi by 2, x by 2, because this is at minus 2 and plus 2. Plus 2, for example, 2 by 2 is 1 and cos pi by 2 is 0. So, right? And then this one refers to the, what is this one? The second one refers to? So, it is 3 pi by 2, x by 2, right? Like this. So, we know that the second one is like this, and the third one, so these are all symmetric. Problem in the sense that everything is symmetric about x is equal to 0 and y is equal to 0. And so that's why we choose symmetric functions. So the symmetric function about x is equal to 0 is this one. So what about the y? So the y, I'll just remove this one. So this is about x, and about y, so that means that about this one, so we will use cos pi by 2 y. So you can see very well that when y is going to take plus minus 1, so it is going to be 0. So that means that it is cos pi by 2 . Obviously, you can see that we don't use terms sine. Why sine we don't use? Because if you look at the sine is an odd function. It is an odd function about x is equal to 0. So that means that it is plus on one side and minus on the other side, so which is unsymmetric, right? Antisymmetric. So that way we know that the terms, even functions or symmetric functions, are like this about x-axis, and this is about y-axis. So then what is that? It is just not x function, so it should be a product of these functions. So it's a, so is are product of symmetric functions about x-axis and y-axis, or we say about x is equal to 0 and y is equal to 0. So that means that we can say now, therefore, so psi 1, how do we get the psi 1? So psi 1, we get it as a product of these two, that is cos pi by 2 x by 2 times cos pi by 2 y. So this is the first term, and the second term will be, in fact, all possible products of these two will be a trial set. So we can write it, we'll take the product of this with this one, and psi 3 is cos pi by 2 x by 2 and cos So like this, we can take all possible products. So this is a set, maybe n terms, or you can make infinite number of terms and infinite number of terms here, and then you can take product of all these things. So once we know of course, you also recall that psi naught has been taken to be, we already took that psi naught to be 0. So we have psi 1, psi 2, psi 3 and all these things. So now our solution will be just based on this one. Just now we derived that what should be the Kij in the set of algebraic equations, right? So Kij is nothing but over the domain, whole domain here, and we have take Wi equal to psi I, psi I. So we have here psi I, and this is L Ij d omega. So we will continue this in our next class. For the moment, I'll just stop it here and we'll continue in the next class. Bye bye.